Alrighty, welcome everyone to day 14 of Advent to Code. Yesterday we took our first L, and in fact we didn't actually complete part 2. Since then though, I have actually gone back and kind of worked with some people to figure out the right solution. So if you check my GitHub now, there is a solution for part 2 up there for code. It is not all my own code, it's kind of worked with some other people, but it does do part 2 without using the Chinese remainder theorem. And it is pretty efficiently. So if you want to look up how to do it in Java, that's not Chinese remainder theorem, go check it out there. I'm not going to explain it because I don't fully understand it. I sort of understand it. It sort of uses the least common multiple in a sense, but at any rate. All right, so we got 1 second here, and day 14 has begun. What do we got? As your ferry approaches the seaport, the captain asks you to help again. The computer system that runs this port isn't compatible with the docking program. I apologize for the train that's about to go by. So the docking parameters aren't being correctly initialized in the docking program's memory. After a brief inspection, you discover that the seaport's computer system uses a strange bitmask system in its initial program. Although you don't have the correct decoder chip handy, you can emulate it in software. The initialization program, a puzzle import, can either update the bitmask or write a value to memory. The values in memory or addresses are both 36-bit unsigned integers. For example, ignoring bitmask for a moment, a line like mem8 equals 11 would write the value 11 to memory address 8. The bitmask is always given as a string of 36 bits, written as the most significant bit representing 2 to the 5th on the left. Okay. The current bitmask is applied to values immediately before they are written into memory. A 0 or 1 overwrites their corresponding bit in value, while X leaves the bit unchanged. Okay. So the following program. This program starts by specifying a bit mask of that. The mask specifies will overwrite the 2 bits in every written value in the 2's bits in with a 0, the 64 bit with a 1. Okay. So the program attempts to write the value 11 to memory address 8 by expanding everything the individuals to the bitmasks is applied. So because of the bitmask value 73 is written to memory, right, because it overrides those. Right. Instead, then the program writes 100k. This time the mask has no effect. This is going to the second one. Okay. Right. Alright, 64 is written. Okay. So, to initialize your fairy's docking program, you need to sum all the values left in memory after the initializing program completes. Okay. Okay, so we need to read line by line, read in the bit mask, and then, so we need to go from, we need to convert from integers to binary. Okay. Right. So, let's first start with just reading in day 14. Let's just start by going line by line. So for string s and input strings, we're going to first take our mask here. We're going to check. We're going to split it on the equal sign. So we're going to do and string here. This is going to be our parts again. S split on equal signs, and we're going to check if parts it is parts 0 trim is equal to mask. If it is, this is what we want to do, and in this case we want to simply just take what's in part 2 here and I guess go through and dump this into an array. Yeah, let's make a char array. So let's do a char array bitmask. So it gave us what the length of it is. It's 36, which is good. So what we can do is we have masks. So then we can go for int I. We have to go reverse. We can't just do a true char array because the bitmask is actually reversed of what we want. Or could we? Actually, no, we could. We could just do char c in parts 1 trim 2 char array. We could do that. Oh, we still need to do. Okay, might as well do this the right way. Chars. This train is taking forever to get Oh, it is going by. Okay. So for int I equals 0, while I is less than chars.length, I plus plus. So should we put these in correct order with the least significant at 0? Probably should. So we're going to do bit mask of bitmask.length minus I plus 1, that is going to equal chars of I. That way we're reversing the order of you'll get in a second. So now we have this assigned. So now the mask has been dumped into memory. So now what we need to do is we need to do an else in this case. But this is a memory, so this is dumping numbers in. So we're going to need let's just do a map. A map should work for you then. You can do integer and integer. So this is going to be our memory. Memory. This should work. Okay, so now we have this else here. So this else is going to be this. So we need, in this case, it's just a mem. So we need to do int index is going to equal the parts 0 substring from so it's 0, 1, 2, 3, so 4. So from 4 to parts 0 dots length minus 1. I need to integer parse this. So basically that's what's going to allow us to do is going to allow us to minus 2 because of the space at the end. We need to do minus 2. But that's just going to take out the first 4 characters here, which is the mem with the brackets, and then read the rest of these up until the last 2, which is the closing bracket, the space. So we'll get rid of those. Now we're just left an integer, so that's our memory location. Now we have the second part, which is going to be int number, which is going to be, again, integer parseInt of parts 1. We'll trim it to make our life easier. So now this number needs to be converted to base 2. So we can do for int I equals bitmask length. Do we need what's the I don't know, my bitwise operations are not the best. Yikes. So if we want to bitwise this, if we want to, this would be sort of like a bitwise and. So here's our number. We need to convert this number into a binary, which we already have done, haven't we? Didn't we already do some sort of binary? Yeah, it was like one of the earlier days. Yeah, unfortunately I don't remember which one. Oh, it was this. Oh, but it wasn't. It was the back front bit, right. I don't think we'll be able to use that. Unless, let's see if I can look at this. Was it day 5? Yeah, so it was day 5. So I'm not gonna be able to use that. So yeah, day 5 was the one that just converted to binary. Really? Wait, I can't use this? Oh, we just did powers, right? Okay. So we have a number. So let me do this. So bitmask. Oh, sorry. I equals 0 while I is less than the bitmask. I++. So we need to take our number and we need to get the specific bit at this location, and that way we can build up our int final num, or let's call this the memory to put in mem. It's whatever. So it's going to start at 0, and what we're going to do is we are first going to check if our bit mask with the char, this is going in reverse, isn't it? Because we're going to be inserting in. So we should be actually be going in reverse, because we're going to be taking number, inserting it in, and pushing it over. So we're going to be I don't like. I'm just doing this in Java. I don't know my bitwise stuff in Java very well. This isn't that bad. I just got to think of how Java wants me to do this. So we have our bit mask. Right. So we need to go through each one, figure out the bit mask, and determine. Basically, so if the mask contains it, we just write whatever's in mask. If not, we get whatever in result. Or whatever in the value. So I guess this should be results. It's probably a better name for this. Whoops, not that. Results equals results. So I can bit shift this one. Right, so and then plus that's not, yeah, +1, right? Bit shift, oh, and 1, or is it or 1? So this is what we sort of want to do. We want to shift it over 1 and then or it on. So this is actually this actually does need to go in reverse. So we do want to keep this at just I. That way when we go through here, we can do a simple check if bit mask I does not equal an X, go ahead and do this within integer.parse int that's a really weird way to do it, but that's because it's just, all right, ignore it. Okay, so then that will do it if our bit mask is X. Otherwise, if it's not that, we need to get the correct binary value out of number. That we do here is we're going to then do map, memory put index and result. So now all that's left is just what we need to do here. Can I do this? Can I do int? No, it's not gonna let me do that. I need some sort of and here. I mean, I guess I could do. Right, so it's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. I can't do that, it's too long. Oh, it needs to be a long. That does need to be a long. That's really weird. Binary into the long. So what then this will do is it'll I should have done zeros. Oh wait, no, it's a 0. And, oh wait, no, 0. And so what we can do here is we do, every time we go with this, we shift this over 1 with a 1 going on to the end. Shift this over 1, and then we do here is we can do, no, it just needs to be 1 with a 0. Sorry. Do that at the end. Sorry. So we do is a number here. I'm not very good with bitwise stuff. Sorry. So at the end here for result, it's this, but instead of integer parsent, we're just going to put in what is ever at number ANDed with our current. Result needs to be a long, by the way. There we go. So that, I think, is what we want. Which this needs to be a long, maybe. And then what's the question actually asking us to give it? Was the sum of all the values left in memory after it completes? Okay, so what we just need to do here is at the end of this is just do a big for loop for long value in memory values. Let's hope this works. I hope I did this right. I'm gonna be very sad if I didn't. What's gonna be an enhance for? Interesting. Okay. And then we can just do sum plus equals value. And we just call lap with sum. Fingers crossed this is right. I don't have much hope. But, oh, well. Oh, it's a capital X, my bad. Capital X, not lowercase x. That doesn't seem right to me. Nope. Let me do with their example code. That's not right. That ain't right at all. Because this is the wrong weight, but this is ending in the wrong spot. That's why. Current needs to start with a 1 at the very end and come backwards. Right, this is the wrong thing. So we need to start at 0, 0B with 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 35. So start of that and then do current this way. That's gonna put a 0 onto it, I think. Please. Closer. Because we want to take the last whatever we're at and go onto it. It's not 1 off, is it? No. My bitwise, I'm not. All right, I'm gonna cut here to when I can figure this out. I can fix it. Cause I mean, I'm close. I just need to figure out what I'm missing here. Okay, I figured it out. The issue was when I was doing this last bitwise and operator here is I was messing it up because it's doing a correct bitwise and, but what it's doing is it's giving us back the 1 or 0, but in its correct spot, not adding it on. So we're in one of these cases, we were basically doing a number and the current, and we were getting 8 back because we were getting a 1 bit in the 8th position, which is wrong. We want it a 1 bit in the 1 position, and then that gets pushed over. So we just do a quick check here that this is greater than 0, in which case it is supposed to be a 1 and all that. So that was my issue. Let's put this back to our code or our inputs. We get that as our answer. Submit that. There we go. I was close. Again, bitwise is not my forte. So, anyways, part 2. For some reason, the C support computer still can't communicate with our factory's docking program. It must be using version 2 of the decoder chip, and version 2 of the decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder. Meaning before a value is written in memory, each bit in the bit mask modifies the corresponding bit in the destination memory address in the following way. If the bit mask bit is 0, the corresponding memory address bit is unchanged. If the bit mask bit is 1, the corresponding memory address is written with a 1, is an X, address is floating. Okay, so for example, that write memory 42 first applies the bit mask. Address, so address 42, we apply the bit mask what's at that address. 4 bits are written, 3 of which are different and 2 are floating. What? What? Wait, what? Is floating. A floating bit is not connected to anything and instead fluctuates unpredictably. In practice, it means that floating bit will take on all possible values, potentially causing many memory addresses to be written all at once. Wait. Hold on, I'm reading this wrong. In version 2, version 2 decoder chip doesn't modify the value being written at all. Instead, it acts as a memory address decoder. Immediately before a value is written in memory, each bit in the bit mask field modifies the corresponding bit of the destination memory address in the following way. Oh, this is for the address. Okay. So it's address 42. We take the mask. We get this result. So then we write 100. After writing the mask, so we write. And then for 26, all of these, so what does the 100 do then? This results in memory address of 3 floating bit values, causing writes to 8 memory addresses. Wait. So then I'm guessing we just write the 100 to that. Okay. So here's part 1. Let's copy this down here for part 2. So our bit masks, all of this stays the same. So we don't need bitmask again. We can just reset. Whoops, sorry. We don't need bitmask again down here. We can just reset memory, clear that out. This can be replaced. That's gonna be a little bit faster. Replace it with that. Okay, so that's be fine. So what's the difference here is that we apply the mask right, but when we do this now, what we're instead changing is we're changing the memory address to which we're writing to. Okay. So what we need to do is we're going to need a list here. Actually, it's gonna be a set. We're gonna do a set. So index is not gonna be there, so we're gonna do a set. Yeah, so set string. It's gonna be addresses. What's, I don't remember the Java, what are the Java sets? I guess we can just use a hash set. So we have addresses here. So what we need to do is when we ever go to here, so when we read in a line here, this is not a mask. When we read this line in, instead what we want to do is we want to edit index, not result. So result goes away. And so instead what we get, this is gonna take me a second to think. So what I'm gonna do is I'm gonna have this set here. Basically the set is going to take in all possible, okay. Yes, we can do this way. And then we're gonna have to do is then inside of this go through, this needs to be the long way. While I is less than bit mask length I++. So what we're gonna do is then we're gonna go through each string s. Oh, but strings are immutable, so we can't actually. All right. Maybe less. Sorry. Unfortunately, it's set. I was gonna do this because it's set, but the strings are immutable, so we can't actually address that. Okay. So we're gonna do let's do j equals 0 while j is greater than j is less than address dot size. And so the first address we're going to put in is going to be, what's the first address we put in? We put it in whatever is, well, I guess it's gonna be kind of empty, isn't it? Do we put in the mask as the first address? Well, no, Lex, that's not. I need to convert the address to. I need to first convert the address to binary. No. Okay, I'm not a fan. This part 2. It's thinking of the right solution to go about this. Where it's 8 memory addresses, so we write 100. So we write 100 to 8. Let's wait. We write 100 to 4 places. So it's only then 2 because it gets overwritten with 1 to 8. That's how that. Okay, so it is like that. So what I need to do is I need to take in the memory address and I convert that memory address to binary as a stringified version, and then go by char. And what we're going to do is, as we go char by char, we're going to basically take the string out of the list, edit it, put them back in. But if we get to this point where we branch, in case we get an X, we're going to have to take it out, but then insert it in twice, one for each version. Yeah. So what we're going to need to do is we're going to need to do an initial for loop of the index here. So for is less than bit mask length. Okay, so we're gonna do this for loop here, and what we need to do is we need to do just like what we did up here. So we're gonna have to do index. I need current again. And so we're gonna get that. And so what we're gonna do is we're going to also have our string. Let's do a string builder. Just make our life a little easier. New string builder. Okay. I'm sure this is probably not the most efficient way to do all this, but it's just the way I can think of do it as I'm trying to go and do this. And we're going to append here this, because this is going to add it on. Or we're starting with the most significant, moving down to the least significant, right? So it's staying in the right order. Reset, we're just resetting current. Oh, current's already up there. Well, I can redo that there. And then we're then moving current over. Good. So moving current over, it's getting smaller, so it's adding in. Okay. So now we in builder, so then when we can do this, we can go addresses, add builder to string. Builder to string. Okay. So good now. So now we can do this again. So now what we do is we just do string s is going to be equal to addresses. We actually need to do this reverse style, because we're going to be adding on to it, so it's going to get weird. Good. Get J. So now that we have the string of the address to edit, what we need to do, size -1. Okay, minus. Okay, sorry. Fixing all of these issues. Good. So then what we need to do is we need to address the bit with the chart at this. So we need to do if we just need to know if the bitwise, if the bit mask at J is an X. If it is, then we need to pull it off, and then we need to check, because if it isn't, we can just skip it. But if it is an X, we need to pull it off and change it to add in the opposite of what's there, because it's oh wait. Oh, but we also need to override. Right, we need to do, okay. If it's not X, okay, so we still need to remove. So we need to do, removing, back remove, okay, so we can't remove. So remove J, address edit, K, and then so in this case here we're going to just do address edit. Is there like a set? Okay, so we're gonna do address edit is gonna be equal to address edit dot substring from 0 to J plus the bit mask of J plus address edits J plus 1 to the end. Substring again. substring. Okay, so now there's our address edit on this. Now we just need to put this back in. So address dot add address edit. Put it at the end. That's fine. We can't do that right. Forgot. We can't reset. Okay. Either way, so there's that. So now we need to do for the X, we need to do both of these. We need to do add on if it's a 0, but we also need to add on when it's a 1. I should probably make these stringified. Cool. So now we're gonna add on all of those on. All right, and then we get rid of these. And then after the end of this, we're going to have, why are you complaining? Okay, not. So now we get the end of this, we're gonna have this number and we're gonna have to go through, we need to, yeah, we're gonna go through string, is there a way for me to do like a removing duplicates in Java? Is this a thing? What's the Java? All right, let's kind of remove duplicates. I'm just gonna quickly just Google this real quick just to make my life a little bit easier. Oh. Okay. It's just a copy. So basically it's a list string. This is going to be the mem addresses. And then we just go for string addr in address in not equals. And then we're just going to first just make sure that mem addresses contains addr. So assuming that it doesn't contain it, this is just remove duplicates just in case. I don't know if we really need it, but just in case. Just in case. Make it look cleaner. Okay, so now we have that. What is this for loop here? So these are these addresses that we are doing here. Okay, yeah. And then go to that. I can get rid of from up here as well. Make it easier. Okay. And so now all we do is we just do memory. We have to do a for loop here again for string addr on mem addresses and put it in. I guess we didn't need to do that because this will do it for us technically. This won't allow us to duplicate whatever. So put those all in, and we want to put number in, not results. Which number needs to be a long, just because. Okay, no results needed. And there we should be good. So now we do the exact same thing, long, it's just sum back to 0 of all those. Fingers crossed this somehow worked correctly. Nope. Number format exception for here. Right, that's address, but it's gonna be in binary. Well, I don't need this to be, so I can just make memory a string. And it's gonna complain here. It's gonna complain, but I can do it this way because I don't care. It's just for the duplication. So complain all you want. I'll just make you that. Next out of bounds 39. Oh, it's not bit. It's bitmask I, isn't it? J should only be used for there, so it's actually I here. These are all I. Oops. I. Let's see if this is right. This is my, yeah. Well, I don't have much hope. No, okay. Let's use their example one again for part 2. All right, what do we get? We get 408. It should be 208, not 408, which makes me think it's not overriding. That makes me think it's not overriding this memory here. For string in memory key sets I feel like it's not editing this. Memory dot get memory dr. Did it? Maybe it did. Why are there 4? There should only be, yeah, something's not right here. It shouldn't be these 4. Are those the right 4 though? So 1101. Those are not even the right 4. There's no 1101 in these. Those are not the right 4, so something is off here. They put a X. They put a Y and a Z just out of curiosity. Make sure it's adding the right ones, I think. That's not right. Wait, what? That's not editing. Okay, well there's one issue. If bitmask I equals X, which only happened in 2 locations. Wait, no, it is working. Oh no, it is working. Never mind, it is working. It is working. Hey, is that just looking at their input wrong? Am I looking at their input wrong? It says 1, so the mask is that. It must be missing. It's not, it's just taking on the bit mask. It's not overriding. Oh, it's an OR. Is the bitmask an OR? Oh, if the bitmask is 0, the corresponding memory address is unchanged. Oh. It's a logical OR. So I guess we need to do this. We need to check if bit mask is equal to if it's equal to 1, I see. That's what I'm missing. If the bit mask is equal to 1 here, it is overwritten with a 1. In which case we can just do a 1 here. Otherwise it is a 0, which means it's unchanged, so we just add back address edit. Now let's try that. Without the Y and Z. Without the Y and Z. There we go. Okay, now let's put our input in. Let's remove the output here. Okay, that's what I was missing. Now we should get a more correct answer. Hey, there we go. Okay. So I probably did terrible today. These weren't... That's actually not as bad as I would have thought. It's still pretty bad. I don't know. Either way, I'm not reading too much. So it wasn't... The questions were just weird today. It was just... Understanding was hard for me. And then bitwise is not my strong suit. But for the most part, I got them pretty quickly. It's just I was missing like one little bit that was holding me up. At any rate, let's... What is this complaining about? Oh, this isn't like how they're duplicates here. Okay. Alright, let's move on to the explanation of how this works and what we're trying to do. So, let me go back to the question. So for the first part, we're doing kind of a bit mask system with memory addresses. So we are given a mask as various lines, and what we need to do is we need to apply that mask to the inputs and then put them into the resulting memory location. So in this case, their example here is there's the value of 11, convert that to binary, apply this mask to where x's leave as is. If it's not x, we change it to what is there in the mask, and then we put that value into the memory location. So to do that, first we have to go through each line. We first parse out whether or not the instruction is a mask, which is just changing what our mask is by simply converting this part to a char array, which I could actually probably even make a little bit smoother. Oh, so much charge length. But basically it's just taking our input in, converting to a char array, and saving that. And then... Do I even need to do this? Can I just do bit mask equals that? I can probably just do bit mask equals that. Hold on. I'm making my life, I guess, to make it a little bit easier. All right, anyways, I'm getting off track. So what we just do is basically we just load in that string into our bit mask and save it as is. Then if we get to a line that's not setting the mask, it's actually applying some sort of the mask to the value to save. We first need to parse out the index, so which is like this part. So we need to parse out where in the memory we're trying to save this number to. We need to parse out then the number that we are trying to save there. And then we have these two variables for result and current. So result here is what we are going to save back in, and current is what we're using to get the specific bit of a number. This is just my fancy Java bitwise stuff. You'll see here in a second. So what we do here is we loop over every single char in our bit mask. So of course, because our bit mask is written from most significant to least significant, what we're doing is we first get the first char, which is the most significant bit in our bit mask. We then see if it's an X or not an X. If it's an X, what we do is we just rewrite with whatever our current number, what the bit in our current number is. We do that is with this number, and then we apply this current. So basically, in this case, the very first term, we are just getting that very first bit. Again, with bitwise operations, we check if it's greater than 0, which means we want to apply that. And then what we do is we get that bit, and then we apply it to the result, but then we will shift result over. So every time we do a step of this, we're shifting result over. That way we are kind of building our results bit by bit as we read it from most significant to least significant. Shifting to left then kind of builds in reverse, if that makes sense. Bitwise is if you get it, you get it. If you don't, I don't think my explanation here is going to matter much. But that's how I'm doing it. I'm basically just having this current value that's going bit by bit. We're adjusting it, we're shifting it over to the right to go from most significant to least significant bit by bit, and then taking that bit out, checking it, and dumping it back in. Likewise here, if it's not an X of our mask, we are just simply parsing out that value and dumping it in the very same way we're doing with this one. And at the very end, what we do is we just sum up all the values that we've put in memory, and we're good. For part 2, same concept for the bit masking. The only difference is that now the mask is being applied to the memory address, and the way we are doing that is again the same way with current. So we first get the memory address as a bit string, or as a binary string, and we do is we take that and then we dump that into address, like an address list. And then what we do is we go through all the bit mask fields again, just like before. But this time, if we get an X, what we do is we take that value out of the addresses list, and then we add 2 addresses back into the list. So we take one out, and there's an X in the location. We take one out. We then set the location at that memory address to a 0 on one and a 1 on the other, and we add them both back. That way, they're going both back in to satisfy that floating point requirement. And then the other options are, if it's a 1 in that location, we just add the address back in, but we add it with a 1 there instead of whatever it was there. Otherwise, if it's 0, we just add it back as was. So we go through all the addresses, we pull that address out, we check what the bit mask is. If it's an X, we add 2 addresses back in, one with a 0, one with a 1 location. If it's a 1, we just add one with a 1 back in, and then add nothing, or we just add it back as is if it's a 0. And then same again, at the very end, we just sum up all the values in these memory addresses. Of course, we have to apply them to each one, but that's how it is. Not too difficult. The difficult part was figuring out how to get here. The solution I don't think is too difficult, but just getting to here was a whole other thing. This is probably the longest day I've spent so far, but at any rate, there's my solution. I know this explanation is probably a bit rough. I'm trying to explain bitwise operations when I know them, but I'm not good at explaining them. Okay, so it's after the fact of when I finished this problem. I was on my Discord talking to people, and thank you to DJ Dovoman, I think that's your name, hopefully I said that right. He pointed out there are inbuilt binary or string, there are built-in binary stuff in Java. I never worked with binary in Java, so I just wasn't really aware of this, or if I was, I just didn't think of it. But mainly there is integer to binary string, which allows me to get rid of all of that like current stuff where I was building up the binary string out of a number. I don't need that anymore, so that can be just taken out and replaced with this. So if you look at my GitHub after you saw this video, you'll notice that this is different, mainly because I have that. It simplifies my code a little bit. I still have the bitwise stuff mainly here with this whole result. I think it's better. I might be able to tweak it and not use this bitwise stuff here, but for right now, I think this is good enough. I'm not sure it would really help me. Maybe it would help me a little bit if I had known about this, but at any rate, I just wanted to point that out, and thank you to him for pointing that out to me, because again, binary, I don't really work with that a lot. So anyways, see you next time. Peace out.